Good morning, everybody. My name is Angelo, and I am a production engineer at Facebook here in Dublin. So my talk today is about how we use Python at Facebook. So this is the agenda is pretty simple, just 3 points. The first point is we look about how we use Facebook, like a high level of how we use this language in the company. And then at the end, we're going to look at one example of a production system we use in Facebook, written in Python. So how do we use it? We basically use it mostly in the infrastructure department of our company. And we use it basically for stuff like scaling out operations or provisioning bare metal servers. We use it a lot for monitoring different systems and services. A lot of internal backend systems are written in Python. We use it for performing load tests on clusters and regions, and also, of course, for data science. And we are going to see an example of how we use Python for dealing with the application configuration management. So, mostly all of the backend code in Facebook is stored into a centralized repository. It's a lot of code, trust me. And basically, most of the Python code is in this repository. And I ran some stats last week. And I found out that Python is the third most used language in Facebook after C++ and obviously PHP. But it's still a lot of code, trust me. It's like in the millions. The thing that we did in our environment is building a tool that you can use to compile programs written in different type of languages. We call these tools fbmake and fbconfig. Think about them as the equivalent of the GNU config and make scripts, or tools, I should say. But the difference is that they are language agnostic, which means that they know how to build software written in many languages. And the goal of this is having the engineers, like empowering the engineers to write code instead of remembering how to run G++ or different compilers for Java. So we extract all that away. What you need to do is basically just write a single text file, which is called the targets file, which is actually a Python script, by the way, where you define your artifacts. So you define what are the binaries you want to compile. You can define dependencies on, if you need some libraries, you can put it in this Python script. And then after that, you just basically launch fbconfig, pointing it to your directory structure, so your project directory, and then run fbmake. And this is going to basically navigate and resolve all the dependencies tree, and then create a makefile in the root of the repo, and just then you can run fbmake to basically just compile your code. So it's this fbconfig and fbmake tools are written in Python, and they are very extensible. So you can actually write modules for supporting different languages. We recently added support for Go, for example, and it was done in a week. Yeah, so the goal is basically to build everything, have consistency in defining projects and having just one single way to build projects in this backend repository. So let's talk a bit about how we build stuff. So we decided by choice that we build everything from head. So this is because we want to reduce the complexity of managing dependencies and versions. So and then also we compile binaries statically. This is for the C++ world. So you all know that statically linked binary is basically one huge binary that contains all the libraries needed embedded in the binary. Okay, so we do that. Why we do that? There are different advantages of doing that. One advantage is that all your logic is basically self-contained into the binary, and you don't need to worry about having shared objects in the box. Install this RPM, install this library. We don't need to deal with dependencies. What you need to do is just take this file, copy it to the production machine, and you're sure it's going to run because it doesn't really need many runtime libraries in the operating installed on the operating system. Yeah, and the only disadvantages of that I can see personally is that you always or usually come up with a large binary, with a pretty huge one. This is not really a problem for us because we kind of strip them, and also we use BitTorrent to move them around the infrastructure, so it doesn't take much to deploy these binaries fleet-wide. So this is obviously for C++, but how do we achieve the same in Python? We basically use what we call PAR files. PAR is an acronym for Python archive. It's not like a new technology, to be honest. You can find some people already kind of using the same technology. So when you write your Python code and you compile it, you end up with the .par file. If you cut that file, if you open that file, you see that at the top of it there is a smallish shell script in Bash that basically deals with extracting all the non-Python code of the file. So it's basically, I should say, it's another file, and inside, after that, there is some binary data that is basically zip compressed. So the top portion, the shell script, does basically extraction of non-Python source files. So like, if you have shared objects or any external file that your application needs, it's extracted at this point. And it is extracted in a directory that is per user, per project, and kind of randomized directory so that you can avoid, racing conditions when you start like two instances of the same script, for example. So it extracts these files. It auto-generates a main.py file that basically reads a few environment variables and knows what is the main module that your application needs to run in order to start. Yeah, so that's pretty much what we do, and basically the Py and PyC files are actually loaded at runtime by the Python interpreter because it uses the zip import module, which is able to load source files straight from a zip file in memory. Yeah, so this is pretty cool. So you end up with a PAR file. It contains all the dependencies, like all the different Python modules, third-party modules, Facebook specific modules. So you just take this file, copy it to the production machine, done. But this kind of slows down development because every time you modify a file, you're back in the old C++ days where you have to compile everything again and test it. So we came up with a different format, which is called lpar, which is basically a directory structure with symlinks to the source files that points back to your repository directory, basically. So you can basically change a file and immediately run an lpar file, and you will see the new code behaving properly. The difference there is that the main.py file has a different behavior, so it knows where to look for source code. It changes a few environment variable for Python so that the interpreter knows where to find the different modules in your home directory. So this is how we build stuff at Python. At Facebook, you see that it's a bit different from the way the community works, is install and people, all this kind of stuff. Yeah, so this is something that I wanted to share with you. So I would like to move now to how we do RPC at Facebook. We use something called Thrift. It's actually open source, so you can find it on the apache.org website. Think about it as SOAP or XML-RPC, but it's way, way easier to use, and I'm going to show you with an example now. So basically, it's a technology that deals with the communication between services, and also it deals with how this communication is done, so how data is serialized and deserialized on the wire. So in this case, when you create a Thrift service, what you have to do is basically create a text file, give it an extension called .thrift, define your service there, so you can define all the different methods that you expose to the external world, and the data types that you need to use in your service and stuff like that. After you do that, you can then run the Thrift compiler, which basically generates language bindings for many languages, so like C++, Python, Go, PHP, Haskell, D, whatever. So it generates code that you can then embed into your client or server and just import it and use it to send commands around from a client to a server and stuff like that. So I was thinking that it would be nice to kind of write together a simple Thrift server. And you can actually find this example on the Apache website, but I've just kind of simplified it to fit all in one slide. So it's basically a service that calculates and it does an addition between two numbers and returns back an integer. Okay, so pretty simple there. So this is what you have to create. So just give it a namespace for every different language you use. Then define a service, and inside the service you can define all the methods you expose, and you can have multiple services in the same Thrift file. So you do that. So if you were outside of Facebook, then you would need to run the Thrift compiler and say, hey, I have this file. Can you please generate me the bindings for Python? And just do thrift-gen py and the file. And you come up with you basically end up with this directory structure, which, as you can see, it's basically a Python module that contains a few files. So the first file, calculator.py, contains the client and the server code. Then you have constants definition and data types definition. And after that, you can see that there is a -remote file. This is actually a script that you can use to query the server exposing this service. So let's say you're writing a server. You write a logic, now you need to test it. You don't need to write a client for it because you have one for free when the Thrift generator generates that. So this is what you would come up with if you were out of Facebook. So then you end up, you have to write the server. It's pretty easy. I wanted to fit everything in one slide, so I removed the import lines, but you can find them in the tiny URL. So you import basically those files I described before. Then you just define your handler, which is basically a Python object that inherits from your service.interface. And then you just define your method, which is the add method, and it does just the addition. Yeah, so after that you just, instantiate that object. You define the socket you want to bind to. In this case, it's TCP 9090. Then you have to basically create a transport object and a protocol object. So the transport object is basically an object that provides an interface to basically do I/O on the wire, okay? And the protocol instead is an object that deals with how to encode and decode the data using the transport object. So we define those at line 7 and 8, and then after that we just instantiate a server object and we just launch it. In this case I used the simple server, which is a stupid blocking single-threaded server, which is only good for stupid examples, but you have many different server types. For example, multi-threaded versions and full-threaded version, async I/O versions. They are all documented, so you can just have a look at the documentation. So this is the server. It's just a few lines, and this is the client, which is fairly similar. You import the same modules, then you basically tell the Python interpreter which host and port you want to connect to. Use the same transport and protocol objects. Then instantiate the client, open the transport, make your call, print the result, close the transport. There is no exception handling here, but yeah, there is no space for that. So I spoke about the targets file, the way we build stuff. So if you were in Facebook, you would just need to create this file. It's a Python script, actually. So you just define you basically define two artifacts in this case. So the server artifacts and the client artifacts. You give it a name, and the name are used as when you define dependencies, you can put the name of these Python binaries or libraries. So you give it a main module, which is what the main.py auto-generated script in the par file needs to call to start your application. And then you give it a list of sources you want to put into your par file and the dependencies. And on the first part, you can see how you actually have the FB config fbmake tools calling the Thrift generation compiler. You just define the Thrift library, give it the name, you define the languages you want to support, and then you can say inside the Thrift file, just use the calculator service, because as I said before, you can have different services in the same Thrift file. So then, once you have this file, you could do just fbconfig, the directory of your project. It will go and resolve all the dependencies, create a make file, and then you do fbmake. And as you can see, it's going to compile everything. And in this case, you can see that it actually produces the par file and the lpar file, and also the dash remote script that I mentioned before that you can use for testing the server. So this is how we build stuff, Python stuff at Facebook. So we can talk a bit about how we distribute the applications around. So obviously we don't use pip and or isinstall because we have this par file, so you just need to copy those files to the production machines. And basically we share the same infrastructure that we use for pushing the front-end code twice a day on Facebook.com. And most of you know that it's infrastructure based on torrent, on BitTorrent. So we basically share the same trackers that the push process uses. We actually modified the tracker to be topologically aware, so basically to optimize the bandwidth usage. Basically that means that whenever one box in the same rack has a few chunks of data from that binary, other boxes from the same rack can just basically pull the data from machines in the same rack, so that therefore optimizing the bandwidth. So the tracker is written in C++, but everything else like CDER servers and torrent servers and the CLI tools that you can use to build the package and publish this package into the infrastructure is all Python. So yeah, we do love it. Yeah. So we spoke about how we build stuff. We spoke about how we distribute the stuff. Now it's time to talk about how we configure applications. So when I'm talking about now is not how we deal with the system configuration, OS level type configuration, but actually how we deal with the application configuration. So we use Python for that. So we actually use Python as a DSL. So DSL stands for domain-specific language. Think about stuff like regular expressions or SQL, or even like CF Engine version 2, for example. So they are specialized languages built for one purpose and one purpose only. In this case, we decided to use Python because it's a generic domain language, and it basically you can do a lot of stuff with it. Think about like Chef, for example. The Chef project uses Ruby as a DSL, which means that in your book you can write code and you can do a lot of stuff. So we use Python the very same way for configuration management at Facebook. And we actually use it for like distributing the application configuration. We use it for data science, how to define the different data science processes. And we also use it for defining our internal services. So the system we use for making configuration for application in Facebook is called configurator. And it's basically a system managed to configure, to manage configuration that are usually smaller than 1 megabyte, and they don't change very often, so like a few times a day. And the framework is made of three different components. The first component deals with configuration composition, so it gives you a way to define your configuration, generate some file that is consumable by a machine, and then also provides you with a framework to validate automatically your config. And the second part is it deals with how to distribute this in a way that basically it is able to detect changes in the repository where all this configuration is stored and make sure that the change ends in the applications, in the servers where the applications run in less than 30 seconds. And then there is another part of the system which is a client library that you can use in your code to basically subscribe to configuration and get automated notifications when something changes in the configuration so that you can reload the config inside your app. So I wanted to provide an example of that. So this is a stupid configuration where you basically define a job, you give it a name, you give it like a priority, which is just an integer positive number, and then you want it to, your application to kind of consume it, okay? So what you would do is create 3 files. One file is the Thrift, it's a Thrift file, different from the one I described before because it doesn't actually describe a service, it describes some configuration, so you only deal with the data structures and data types. So in this case, we create a data type called job, we give it a name, and the scheduling is another object, which is a scheduling object and has a priority integer number. So you have this, then you can write a Python configuration file, which is basically Python code, where you imported the Thrift schema, as you see in the first line. Then you basically instantiate the job object, giving values to it. So you give it a name, in this case a job name and priority of 3, and then you just export this configuration. And the third file is a validation file where you can write logic to validate your configuration, and it's going to be executed automatically when all this information is combined together to produce a JSON file. So the validator script is just a collection of functions really that you can link to the objects you defined in the second file. So you can see here we defined a validate job that takes a job as an input and it validates that the name is not empty and that the priority is a positive number. And then in the last line you can see that we actually attach this validation function to the myConfig object, which is defined in the second file, in the blue file. Okay? So you get all of this together. You run a CLI tool, which is basically processing all of this together, and it generates a JSON file. So this is the composition phase of the framework. After that, you get your change, and you actually ask for review. So you basically have a git diff, and you push it to our software review tool, where you can actually ask a human to have a look at it and see, if it makes sense and get approval for it. Once you get approval for it, you push it to the magic infrastructure, which would require a different talk. But yeah, it's just think about it just as a black box that ingests this configuration and makes sure that it is basically spread across the fleet, so in every cluster, in every region. So this is the distribution phase, and the last phase is the client library that you can use in your application to subscribe to the configuration and get notification. There is a small daemon running on each box that you can talk to via Thrift. You can say, hey, I want to subscribe to this, can you do it? So you wait, typically a few seconds, you get this file, and that's done. And the file gets stored in the disk as well. So if there is like some outage with the configured infrastructure, you can still load your data off the disk. It's probably going to be stale if you make a change, but it's good enough. And this is an example of a simple function that you will write in your Python application to subscribe to a configuration. So you just instantiate the configurator Thrift client. You just say start monitoring this configuration, and then this is the callback. Just call this function whenever you get an update, and happy days. So what are the benefits of doing all of this? It seems very complicated, but there are benefits. The first benefit is that every single change goes through a code review process. So we treat configuration the very same way as we treat code. So you have to ask for approval, get one of your peer approving or suggesting changes. So we all know that sometimes you make a change, it seems very simple, and you believe it doesn't break anything, but it can actually bring down an entire cluster or whatever. So you want basically a human to have a look at it, and on top of that you also have validation, automated validation that runs every time you generate the JSON file. And because this is code, you can abstract all the complexity away and build libraries that do generic type configuration and give it to other teams. So that's pretty cool. You can write your functions to do many different type of configuration, and put it in a shared directory and just post it into internal group and say, hey, I have this new library, feel free to use it. And also this gives non-engineers the possibility of changing values in the configuration without knowing how it works. You just give us abstractions and other people, either non-engineers or other engineers, can use. And then the other advantage is that because you have this callback mechanism, you don't need to restart your application if you want to. You don't need to restart the application to pick up new configuration changes. So that's about how we use Python as a DSL. And we can talk a bit about how we do code review. Obviously, all the code is peer-reviewed. We use a tool called Fabricator. It's an open source tool that was started in Facebook. You can download it from that URL, and it supports Git, SVN, and Mercurial. We do kind of enforce some of the PEPs, and basically they are push blogging. So that means that if you don't pass all of the required PEPs, you can push code to the remote repo. And we actually encourage people that if you've written some library that you think it might be helpful for other teams, we encourage you to store it in a specific common directory to basically share your libraries with other people. And basically, we use a lot of unit tests, and when you push your change to Fabricator for a review, you have a clear view of what is green and what is red, and you should not push stuff, if there is too much red, but not everybody do it. Okay. So I wanted to share a few suggestions that we use internally for doing code review. The first part, this slide is about suggestions for people making code review. So the first suggestion is that when you review code, you should not review code thinking how you would write that code. Everyone has his own style. You still have to follow some guidelines, but you should not be that picky, and you should let people move fast and kind of ship stuff without being too picky. Yes, the other suggestion is that if you review a diff and you only actually are providing nitpicks, kind of suggestions, it's not really a good review. So you should kind of avoid just to do reviews that are just a collection of nitpicks, because people want to ship stuff, they might get a bit frustrated, and so because of this, you should also avoid kind of having a lot of discussions on a Fabricator diff, and and just kind of walk to the desk and have a chat with the guy that is writing the code, because we all know that sometimes people behind keyboards can be evil. and the other suggestion we have is that you should try to emulate people that are good at code reviews. That's pretty obvious. So from the side of whoever is writing the code, we actually suggest a few things. One thing is that you should only make, if you have a complex task, you should try to split all these tasks into different subtasks and have one diff for each one of them, because it makes the code easier to review for other people. And the second suggestion is that you should always aim to improve the code base, which means you can improve it by adding new code, you can improve it by deleting code, you can improve it by fixing bugs, but your goal should always be to improve, not to cause regressions. Then the other suggestion is mix and match reviewers, which means try to put in your diff people that are outside of your team, because people inside your team have kind of an interest in getting the stuff shipped. So if you get people from other teams, you can get different point of views. They might know the language better, so it's always better to do that. And then the last suggestion is don't take stuff personal. You are not the code you write, so just be aware of that. So we are almost at the end of the talk, and now I'm going to give you an example of some Python project that we use in production. The project name is Keanu. It's an automated tool for performing load tests of clusters and regions. The name comes from the 91 movie Point Break, starring Keanu Reeves. The way we use that name is because the goal of the system is to find the breaking point for each cluster or region or a bunch of hosts. Because only doing that you actually can, you can actually find the real capacity of that bunch of machines. So we do that by basically changing the ratio on the global load balancers to push live traffic on each one of those entities. And basically there is like a feedback control loop that looks at some predefined metrics like, I/O, CPU, so system level metrics, but also application level metrics. And basically watches those metrics until you basically you basically go just above the acceptance level. So when you go up that level, you just basically back off immediately, and you have this number that is basically the real capacity of your cluster or bunch of machines. So we run that daily, typically when it's peak time and when there are no incidents, and we don't do that on drained cluster because it doesn't make sense. Yeah, and basically we also do that at regional level because often you can find that the sum of the front-end cluster capacity doesn't always equal to the real capacity that you measure because there are so many different variables there. Yeah, and of course, because we actually watch those metrics, we use it as well for raising alerts and alarms when paging people and stuff like that. Okay. So basically, why this was actually written in Python, and we really like Python for this because it basically allows us to be flexible. So this started as just a load testing framework. Then it evolved into a regional testing framework. Then it evolved into a drain tool for draining racks in a controlled way. Then it evolved into a warm-up tool to bring it up again. And then it evolved into a single server load tester and back-end load test tool. So basically Python allowed us to code this very quickly, because it's a very flexible language. And it also allowed us to be quick in responding to changing requirements. So, for example, we needed to change from a monitoring system to another monitoring system, and we could do that in a few hours. And we found a bug during one of our recent region fire drills, and we were able to basically fix that very quickly because the language just allows you to do that. And the other thing is that when we started this project, we were not really focusing on unit tests. So these unit tests were added after that, and we were able to do that in a very quick way.